In Physics 1, you covered at least the things that are listed here. Let's go back to the beginning and kind of review where our understanding of physics ought to be at this time. Okay, we have four basic undefined quantities in terms of which we define all other quantities in physics. The concept are the quantity distance, which we measure in meters, the quantity mass, which we measure in kilograms, the quantity time, which we measure in seconds, and the quantity charge, which we measure in coulombs. Now this might be new to you. You might not have studied this first semester. In my classes I don't talk much about charge in the first semester, but charge is measured in coulombs. A coulomb is the magnitude of a charge consisting of approximately 6 times 10 to the 18th electrons, or if you prefer 6 times 10 to the 18th protons. From distance and time, we define velocity, which is the rate at which position changes with respect to time, or displacement divided by time, or the derivative of position with respect to time. We define acceleration as the rate at which velocity changes. For calculus-based students, that's the derivative of the time derivative of the velocity. Force by Newton's second law is related to mass and acceleration, F equals ma, showing us that for a given force, a greater mass gives us less acceleration, and so forth. We define energy or work and energy being interchangeable quantities, as the product of force and distance. Work is the product of force and distance. I guess we think of energy as the ability to do work. So it's equivalent to a force times distance. We define momentum as the product of mass and velocity. And momentum is what gives an object effectiveness in a collision. Momentum is the quantity that's changed by an impulse. What's an impulse? An impulse is the product of force with a time interval. The force multiplied by the time over which it applies, or at least the average force multiplied by time. In calculus, the integral of the force over time. That's the impulse, gives us the change in momentum of whatever object the force is being applied to. We have torque, which is a kind of a twisting force, and we recall that's defined as the force times the moment arm. Angular velocity, the rate at which the angle of a rotating object changes. Angular acceleration, the rate at which angular velocity changes. The big conservation laws of mechanics, conservation of work energy, conservation of momentum and angular momentum, and the implications of those, and those are laws that you should have studied to great length. Maybe not so much angular momentum, because that one gets pretty difficult to analyze, but you should at least just understand how in astronomy, in the universe, how a rotating gas ball, as it gravitationally collapses, gains greater and greater angular velocity as a result of the conservation of angular momentum, or how a figure skater, when he or she brings arms in close to the center of the body, will increase the velocity, the angular velocity of a spin. And of course, these laws are the direct result of Newton's laws, Newton's first, second, and third laws, which are things that we should understand very well at this point. We studied vector quantities, and vectors are going to be very important, especially in the study of electricity and magnetism. Forces and the natures of different forces, gravitational forces, contact forces, action-reaction pairs, and so forth. Don't have room to list all the types of forces we have here, but you get the idea. Different types of motion. We have circular motion, simple harmonic motion, orbital motion, and the way different systems behave. Now that's the topics that we looked at first semester. As we go into second semester, when we introduce charge into this scheme, then we get current, which is the charge passing a given point and divided by the time it takes to pass. Average current will be charge divided by the time interval. Electric field much analogous to a gravitational field by Coulombs' law, and we'll see where that comes from. Magnetic fields. The idea of power in an electrical circuit. Okay, how does power get from the power station to you? What is the power? The idea of voltage, resistance, capacitance, and inductance, and I'm not going to talk too much about these, but kind of think about these terms. Coulomb's law, which tells you how static charges affect each other. Ampere's law, the law of Biot-Savart, other laws involving electricity and magnetism that tell us where magnetic fields come from, how they're set up, how they respond to electric fields, and vice versa. The idea of a time constant in an RC circuit, the idea of resonance in an RLC circuit. Okay, these are important topics. Now there's some more topics that we'll cover that we'll at least talk briefly about in the next video clip.